reject the null hypothesis that mu equals 20. Now you're not quite done yet. You have to go back to what your hypothesis said and what were they trying to claim on this. If you reject that the mean equals 20, then what does it say about the claim? Well, think about it as you reject that mu equals 20, so that means you can support the alternative. If we're saying that mu equals 20 is no good, then mu is greater than 20 is good. Okay, so we support the claim that mu is greater than 20. It appears the machine is dispensing more than 20 ounces on average. Now again, remember, this is all based on that one sample of 50. And because that sample of 50 results in an X-bar distribution, if you did the repeated sampling, it all goes back to that central limit theorem and using sigma of X bar and mu sub X bar and making that distribution of X bar where we're assuming that the center was 20. That was our null hypothesis. And then we collect our evidence, and our evidence told us that our sample mean of 20.05 was too far away from 20 to say that 20 was a good assumption to make. Okay. Suppose we change the significance, number 7, suppose we change the significance level to 0.01. What is our decision now? Well, if we change to 0.01, well, let me show you right on the diagram I have here. Instead of alpha being 0.05, now we're going to say it's 0.01. So now 0.01 is going to be less than 0.0384, which means we're going to have the area being like over here now, here to the right, for an alpha value of 0.01, which means if we only wanted a 1% chance of saying that 20 was a faulty assumption for the population mean, when 20 really is the population mean, okay, now 0.0384 is close enough to 20 to not reject that original idea. Okay. So if the alpha value is 0.01, 20.05 for X bar was not an unusual value because that had a 3.84% chance or 0.0384 probability compared to 0.01 probability. So there, we're close enough to the mean. And again, we're ignoring this green mess here. Okay, comparing this value here to this value here. Okay, this is close enough to 20 compared to this one. Okay, so we would fail to reject HO in that case. Okay, or not reject HO. Okay, so our decision, if alpha was 0.01, 0.0384 is greater than 0.01, so P is greater than alpha, which would tell us not to reject the null hypothesis that mu equals 20. So we cannot support the claim that mu is greater than 20. Okay, so there again, when you go back to your hypotheses, if we're not rejecting that mu equals 20, we're saying that mu equals 20 is okay, which means the claim is not okay. Okay, so we cannot support the claim that mu is greater than 20. Okay, another example. Okay, we'll go through these other ones faster. I have them all worked out just for the sake of time here. Okay, now suppose you want to do the same example, except now we're looking at collecting 50 bottles with a mean of 20.05, which is the same as before, except now we're claiming the mean amount of soda dispensed was different from 20 ounces on average. So here we need to pay attention to the concept that we may be on either side of the hypotheses, of the null hypothesis. Okay, so when you set your hypotheses now, different from 20 is not equal to 20. Okay, because it's not saying just greater than 20 or being less than 20. Different from 20 means not equal to. Okay, so that means your alternative hypotheses would be that mu is not equal to 20, which is what we're claiming. And then the null hypothesis, again, always claiming equals. Okay, that mu equals 20 here. Okay, so now that we have our hypothesis set up, we calculate our test statistic again. Now our test statistic is not going to be any different than it was before. Okay, so I don't want to get too far ahead here. Okay, the test statistic, nothing was different than before. We get 1.77, okay, for our z-score. when we go to our diagram, okay, this one is a little bit different. Okay, because we can be on either side of mu equals 20 because of the different from 20 meaning not equal to 20. Okay, when we started this off, before we collected our sample and got a mean of 20.5, we had no idea what to expect. Okay, we just knew that we were looking at being different from 20. So that means if we were far enough below 20, then that would be a problem for our assumption of 20 being the mean. Or if we were too far above 20, that would be a problem for our assumption. So now, when you have this different from corresponding to not equal to 20, we shade on both sides here, or in both tails. What's different here, though, is you take that alpha value of 0.05, and you have to split it between the two ends. Okay, so that means if you take 0.05 divided by 2, or alpha divided by 2, you get 0.0250. So that is the area to the left of whatever x bar value this is, or to the right of whatever x bar value this is. Now what we did, we have the same z-score of 1.77. Okay, so on the z-axis, we have a z-score of 1.77. Our x bar, our sample mean was still 20.05. Now when you compare that, the probability of being greater than 20.05, that was 0.0384. Okay, notice that if you compare that to the 0.025, okay, again, which was alpha over 2, okay, that 0.0384 goes farther into the data here, okay, coming from the right-hand side, farther in than the 0.025 area does. Okay, so that means that 20.05 is close enough to the 20, where the assumption of 20 being the population mean was an okay assumption. Okay, now what's a little bit different here, that your book will explain a little bit differently than I do. Okay, what your book will do is in the Moore book, they'll say when you look at your decision, okay, I looked at it as comparing our 0.0384, okay, again, which came from looking up the z-score of 1.77 and being more extreme than that. I compare that to alpha over 2. Well, that's the same thing as looking at multiplying each side here by 2. If you do 0.0384 times 2, your book will say the p-value is 0.0768 and alpha is 0.05. Okay, and obviously it's fine to do it that way. Okay, but I just want to point that out, that the way I explain it is you compare the probability of being at extreme as 20.05, compare that to alpha over 2, but it's essentially doing the same thing. It's just instead of dividing alpha by 2, you're multiplying that probability by 2. But your book will call the p-value equal to 0.0768, not 0.0384. Okay, so just be careful with that when you're doing examples out of the book. Okay, so what does that tell us? Well, again, the 20.05, or the z-score of 1.77, is close enough to 20 based on our alpha value of being 0.05. Okay, we split it between the two ends. So 20.05 is close enough to 20 where we do not reject the null hypothesis that mu equals 20. And what does that tell us about the claim? If we do not reject that mu equals 20, then we cannot support the claim that the machine dispenses different than 20 ounces on average. Okay, moving along with some different examples here. Okay, again, this video is getting long. Okay, but this is a huge topic, so it's an important topic. Okay, if you read number 9, this is where I'm going to say you can pause the video, and I'll just put the answers up, because if as you go through these, you have to pick out the values for your x bar, use of x bar, and sigma, and okay, recognize what alpha is, and then they're set up all the same. You're going to write your hypotheses. You're going to calculate a test statistic, figure out where it is, okay, where that test statistic is, and then make a decision based on that, where that test statistic is and its p-value. Okay, so read number 9. Okay, and I'll put the answer up. So if you need to pause the video, go ahead. And I'll put the answer up, and I'll explain a few things in the answer, but try to do it very quickly. Okay, so pause the video, read it. Okay, so the null hypothesis was that mu equals 1.5. The alternative is that mu is greater than 1.5, because they're saying that mean reserve capacity of battery is greater than 1.5. So that's what they're claiming, is that mu is greater than 1.5. You find the test statistic by doing x bar minus mu sub x bar divided by sigma over square root of n. That gives you a z-score of 1.05. And we're looking at mu being greater than 1.5. So we're looking at the right-hand tail, or the right tail of the distribution. If that was mu is less than 1.5, then it would be shaded to the left over here and not over this way, to the right. If that was a not equal to, so if they claim that their mean reserve capacity was not equal to 1.5 hours, it'd be shaded on both sides. And this alpha value of 0.1 will be 0.05 now to split between the two ends, if that was mu not equal to 1.5. Okay, so we found our test statistic to be 1.05. And in terms of our where that is on our axes, well, 1.05 for the z-score is the same location as 1.55 for the x bar value. And we can see the probability of x bar being greater than 1.55 equals the probability that z is greater than 1.05. Greater than, we're going to do the 1 minus. Okay, so when you look up 1.05 in your z table, you get 0.8531. And 1 minus that will give you 0.1469. That value is larger than 0.1000, so there's more area there. Okay, there's more area included there for the 0.1469. So what that tells us is that 1.55 is close enough to 1.5 to tell us that 1.5 was an okay assumption to make for the population mean. So that means that we do not reject the null hypothesis. Okay, so we do not reject HO, that mu equals 1.5 hours. And if we do not reject HO, so if we're saying that we're saying that this idea is okay, that mu equals 1.5 is okay, we cannot support the claim that mu is greater than 1.5. Okay, the last couple here. Okay, and again, I'm sorry this is running over so much. Okay, so read number 10. Okay, I'll put the answer up here. Okay, so they're claiming that the decrease of cholesterol levels by more than 34 points. Okay, so more than 34 points. They're trying to say the mean decrease is more than 34. That's what they're claiming. Mu equals 34 has the equals. Okay, so that's your null hypothesis there. Mu equals 34. Okay, so when you find your test statistic, oops, and I should have said hypothesis or hypotheses, test statistic, and then decision. Okay, so those are the essential parts of a hypothesis test. Okay, we calculate our test statistic. X bar was 37 because that was our sample mean. Okay, so they took a sample of 100, mean of 37, so that's X bar, minus mu sub X bar, okay, which we have is 34, because remember, mu sub X bar is the same thing as mu because we're looking at the x-bar distribution. That's right in the center. Divided by sigma over square root of n. Okay, those just coming from the question. So we get 2.59 for our z-score. So the probability that z is greater than 2.59. The reason we're looking at greater than 2.59 is because they're saying that mu is greater than 34. So we're looking at to the right-hand side here of the distribution. Okay, so the sample mean there was 37, so that was the value 37 there. Oops, I'm sorry. This was value 37. Okay, 0.01. Okay, that was the alpha value. So our x bar of 37, the probability that x bar is greater than 37 equals the probability that z is greater than 2.59. So you do 1 minus, when you look up 2.59 in the z table, you get 0.9952, which is 0.0048. So the area from here to the right is 0.0048. So what that tells us is, as far as our decision goes, p is less than alpha, so our p-value of 0.0048 is less than 0.01, okay, which means that we reject HO, that mu equals 34. So we're saying that 37 is far enough above 34 to reject that 34 was a good assumption to make for the mean. So that means we can support the claim that mu is greater than 34 points. Okay, now your book will talk about this. I'm doing on the Stat Tutor videos about when you're looking at some more serious consequences, you want small significance levels like 0.01. And a lot of times they don't even give a significance level. They'll just give a p-value in their research and then let the people decide, or doctors or whoever decide, whether or not that's a small enough p-value or not. Okay, so you don't want to have like a 10% chance of making a type 1 error when you're talking about drug pills, okay, because that's a very serious thing. When you're looking at like running a marathon and you're looking at average lengths or average times, maybe it's not as serious, okay. But when you're looking at lowering cholesterol or blood pressure, okay, things with drugs, you want to be you want to have smaller alpha values or smaller p values to compare to.